Okay. So, if you recall, I promised that today definitely I'm going to start, solving some partial differential equation. So, let me start with or equations of this type. Okay. Is it a PD or OD? Can anybody tell me whether this is a PD or OD?
OD.
OD, right? You know, if you look back at the origin of this differential equation, so it came from dx dt, right? Although we are considering a function of several variables, still this equation is an OD. You have to remember that. Okay. So now, because you are already, conversant with the methodology of solving this equation, so I'm not going to discuss that in detail because you already know it. But what I'm going to do, I'll try to solve a couple of problems in such a way that the understanding of the geometry becomes more clear to you. Okay, fine. So how to find out this solution. Like say, what we can do, we can choose a pair of these ratios, right? And suppose I am choosing this first pair of ratios. So then what I'm going to do from these two ratios, I would try to find some functional relation, like say phi xy equal to c1, right? And then what I'm going to do, I'm going to substitute this one here somewhere, and then I'll try to make use of again another two ratios, which definitely must include the third ratio, right? And we'll try to solve the problem, right? So that is one way, and the other way is simply using Lagrange's multipliers. Did you do we call it Lagrange's multiplier or simply multipliers? Okay. Anyway, you know the methodology. Okay. So now, and again, let me tell you another thing. See, all along, whenever I have been telling you to look at, the book, I'm still maintaining that it is, CMOS. Huh? In fact, now in PD, this book I am referring to is simply this one. Huh? Jite and Thor. So maybe I'll refer it to simply Thor, right? It is easier for you. Okay, fine. So now let us take a very easy problem. It is, let us try to work on this exercise. Okay, so dx by y plus z dy by y equal to dz x minus y. Dz x minus y. Okay. Fine. So now, can you tell me how to go about this, or where have you been through? Yes. See, in fact basically I have through here and here. So here you can see y plus j. So if I do say dy plus dz, so then it is going to divide it by what? X, isn't it? Is it okay with everybody? Dy plus dz. So in the denominator, if you add them, what you get? Simply x, right? So, and obviously, because I already have y plus j here, I can simply use dx by. Am I okay or not?
Yes, sir. You are okay.
I'm okay, right? I should be okay. So, what does it give you? What does it give you? So this implies your x dx and then minus your y plus z dy plus z. This is equal to 0. So from here, I get one solution. What? X squared minus y plus z squared equal to c1. Okay, fine. And what about the other one? Where do we have a clue? Again, if you use a dx minus dy, because I have this x minus y. So dx minus dy, is it going to? Let me see whether I have written it correctly. Something seems to be missing here. Just a minute. Yeah, y plus z, x minus y. Okay, it is fine. Yeah. So okay, fine. So what about the next ratio? Can you give me another ratio? So dx minus dy, definitely it is going to give me something. Yeah, at the denominator I am going to get j, right? Is it okay? Fine.
Yes, sir.
Right. So again, dx minus dy, obviously it is going to give me j. So this is equal to dz x minus y, and from here, basically, eventually I am going to get what? X minus y squared minus j squared equal to c2. J squared equal to c2, right? Can you get more than that? Can you get something more than that? X plus j.
dx plus
In fact,
dj.
yeah. In fact, I can take it more. So this will also do, because I want to work with some easier explanation. Easier expression. I'll tell you why I choose that. Why I choose that. Obviously, they are going to do. Don't worry about it. They are going to do. Don't worry about it. So maybe like say dx plus dz also. Y will be going. So it is going to be x plus z. Yeah. So I have a much. Yeah. So okay. So from here I can get something like x plus z by y equal to say c3. Yeah. Fine. Okay. Fine. Say I can choose any of these three pairs. I can choose any of these three pairs, right? To intersect. In order to get what? In order to get. Okay. That's
Solution.
One, right? Okay. Solution. Okay. That solution is what I'll come to that later on. Okay. Fine. See now for the time being, let me concentrate here. So I have got something like say u xyz equal to c, right? I have got something like u xyz equal to c. So now, if I look back at my original equation, say suppose I use y plus z, y and x minus y as component of some vector field, say y plus z, y, x minus y. Okay, so now let us simply use this. I can guarantee you that the same conclusion you'll be able to draw out from these two also. Okay, I am using this because this is similar to walk out. Okay, so now let me still keep them. Now, suppose I do like say grade u dot viewer. So then grade u So here your u is x plus z by 1, right? So then it is simply pux plus qy plus rqz. Okay, so p is simply y plus z. Now this is simply what? 1 by y, right? This is simply 1 by y, and then q is equal to y, and this is going to give you your x plus z by minus y squared, and then what you get r is your x minus y, and that is simply 1 by y again. Oh, so 1 by y. It's okay with everybody, right? I can just see 2 is good enough for me, 2 relation. Okay, fine. So if you work this out, eventually you will see that this is going to give you 0. This is straightforward. Is it okay? Fine?
Yes, sir.
Right? So what does that tell you? What does that tell you? Whenever you are going to work with equations like this, the solution is going to give you some function. In this case, it is a function of 3 variables x, y, z, and that function is nothing but a first integral corresponding to the vector field represented by this P, Q, and R. Is it okay to everybody? Right?
Yes, sir.
Yes.
Right? And then the next thing is, say, from here, in this particular case, I have derived 3 first integrals. I don't know whether the others have first integrals or not, but they have to. I can assure you. I can assure you that whatever solution you are going to get here, right? So that is going to represent a first integral of the vector field corresponding to those entries P, Q, and R, right? Okay, fine. So this is also a first integral. You can easily check that if you work this out, again you are going to get that grade u dot b to be equal to 0, right? Okay, fine. And then what is going to happen if, say, suppose I call this as u1, and suppose I call this one as say u2 x, y, z, say, suppose this is equal to this. So then, now the next thing is that you can definitely check in this particular case for grade u1 and grade u2. Okay, grade u1 cross grade u2, right? And you can check. I mean, where this gradient vector is going to be non-zero. Okay, so what I'm telling you is that yesterday also I worked out a couple of examples. So now once you have found out 2 first integrals from this equation or from equations like this, so then what you do, you check this, right? And this is going to give you a certain domain omega in R3. It is going to give you a certain domain omega in R3 because I want this to be non-zero. Okay, so in that omega, you will be able to find out what? An integral curve, isn't it? Right? Because yesterday I worked out one example, or I told you that if this is non-zero, it is non-zero. Definitely, you will be able to find out a curve for which, again, you can have a parameterization. Is it okay with everybody? Fine. Yes. Is it okay with it? Right? Yes, so you should remember that although I mean this is merely a very simple equation. I mean, very easy to solve, right? There are a lot of stories hidden behind that you have to remember. Okay, fine. I hope now you can relate the geometry with this particular equation. Is it okay? Is it okay with everybody?
Yes, sir.
Yes,
Now,
sir.
yes, thank you. See, now the next thing. Yesterday I worked out another theorem. So I'll just verify that theorem. I'll just verify this theorem. See, I have already told you that if you can find one integral, one first integral, you'll be able to find out infinite number of first integrals, right? So basically, if the function u(x,y,z) is a first integral for the vector field V, right? So then any function f of u is again going to be what? A first integral of the same vector field. So now let us take this. Let us take this function. You simply define your f of u. I am simply flipping it. Is it okay with everybody? Right? Just simply by flipping it, I'm creating another function. Is it okay? Are you getting my point?
Yes, sir.
Yes, sir.
Yes,
That's
sir.
what I'm trying to say. So now let us check whether this is a first integral for this one or not. So then what is going to happen? What is going to happen? Like if I want to check, I mean, grade. Say suppose this is W. So now I have to check. So this, what is this product? So then what I'm going to get from here, minus y x plus z square into y plus z, and then plus 1 by x plus z into y. Okay, then again it will be the same thing. It will be minus y by x plus z whole square, and then into x minus y. Okay, so then obviously this from here what I get, minus y square minus yz, and this is simply you multiply this by x plus z. So plus xy plus yz, right? And from here minus xy plus y squared. So now you can see that this is giving you 0. Is it okay?
Yes, sir.
Right? So we have
Yes,
verified this theorem. So now I think this particular example has unfolded many things, right? Now you have concepts of the integral curve, then first integral, okay, and again that condition, the cross product of the gradients of the integral curves not being 0 is going to give you an integral curve. Okay, fine. So yes, so what I would suggest you try to work out the examples from this book, Thor book. There are many. So just a minute. Yeah. So basically, now see, whenever you are given an equation like this, say suppose you are told to find out the integral curve from that system of equations. As I have told you that you can always associate, what a vector field. You can always associate a vector field to the equation given by this dx dt equal to p, dy dt equal to q, and dz dt equal to r. So now I think the understanding of the meaning is better. Okay. So and whenever you are told to find an integral curve of some vector field, so what you have to do, simply find out two first integrals, right? As you have seen that you can find out infinite number of first integrals, right? You simply find out two first integrals and check for their cross product of their gradient being non-zero, find out the domain, and then claim that this is an integral curve defined in that particular domain. Is it okay? Fine. See, earlier it was very easy, right? I have emphasized, probably you guys are angry with me also, because I have been telling you this over and again, that 10 out of 10, oh my God, it is so easy. But as I have told you, there are a lot of hidden stories, or there are a lot of stories hidden behind that equation. Okay, fine. So now, because we already know about these integral curves, so that brings me to the general solution. This of this equation. That brings me to the general solution of this equation. And again, let me tell you, sometimes I may miss some crucial information. Like say, I told that this vector, I told you about this vector, but you must remember that the vector has to be non-zero. At least one of those P, Q, and R, it has to be non-vanishing. Okay, fine. So now, can you tell me, I mean, what does this equation tell you? I mean, basically, this is P is a function of x, y, z. You know that. I mean, similarly, x, y, z, e, y plus r, x, y, z, e, z equal to 0. Okay. So suppose this is this is an equation, and I am seeking a general solution for this equation. So now, whatever discussion I had in today's class, can you tell me something about, suppose you are able to solve this equation. So that means we are solving this equation for u, right? We are trying to find a function u of 3 variables x, y, z in such a way that this function satisfies this given differential equation 1. Okay? So now, can you tell me something about this solution u? Something about this solution u. Yes. I have told you many things today. You should have enough. You should have enough information. Yes? Yeah.
This will be a first integral corresponding to the vector field PQR.
Yes. So basically what you are saying is that the solution that I am going to find out, because this equation is nothing but grade u dot PQR equal to 0. Now, so that means if I represent this vector field by V, okay, so that means with this solution, there is always an associated vector field, right, which is connected to the differential equation. Yes. Is it okay till now?
Yes, sir.
Right? Okay. Now, can you realize, or not can, do you realize that earlier, probably you had solved equation like this earlier also, right? Okay. Did you solve it earlier? I mean, in your MSc days, this kind of equation?
Yes, sir.
Yes,
Yes,
right?
sir.
Then what you simply did, you solved this equation, isn't it?
Yes, sir.
At that time, did you understand why did you solve that equation?
No, sir.
Do you understand it now?
Yes, sir. Now I could understand.
Say, I want the yes answer from everybody. Now say it is so easy, isn't it? It is so easy. The geometry, understanding the geometry associated with the given differential equation is very easy, right? We have to be systematic. That's it, right? I'm very happy that now you have understood it now. Okay, so that's what it is. Whenever you are told to find out the, solution of this equation, you got to simply solve it. You know why you got to solve it. So basically, you got to find out the first integral of the vector field given by this equation. Okay, and you know how to find out the solution. That's it. Okay, so now, and here I'm not even concerned about integral curves and so. Okay, here I'm simply concerned about finding out some function u of x, y, z which satisfies this equation. That's it. Okay, so you already know how to find out the solution, right? I am going to write two theorems. First theorem, in fact, we have already proved. First theorem we have already proved. The second part I am going to prove, which is which look more difficult than the first one. But once I do it, you will see that it's very easy. Okay, fine. Theorem. Let your U1 and U2 be solutions of the equation simply this one. Pux Qy plus Ruz equal to 0. Let me call it 1. And in some domain, this R3. In some domain, R3, and again, let your be A, and of course, here I am assuming that PQR, at least one of PQR is non-vanishing. That I have assumed. Okay. Be a C1 function of say two variables. When you will see the last statement, you will see that, oh my God, it is so easy. We have already done it. Okay, so then this one. If I create a new function again in those three variables x, y, z, out of these solutions, this solution is again a solution of 1, and 1 in that omega. That okay. So right, we have already done this right yesterday, isn't it? We simply proved it in
Yes,
terms
sir.
of first integrals, isn't it? So now the given equation is nothing but the definition of first integral for a vector field V, whose components are given by P, Q, and R. Is it okay?
Yes, sir.
Right? See, now sometimes although it is pretty straightforward, sometimes the next theorem that I'm going to state, it may be a bit not really difficult, like say confusing to understand what is the difference between this theorem and the theorem that I'm going to tell you about. Okay. Now say this theorem merely says that okay, if you have an expression like this, that is going to be a solution. Okay. Now, what is the guarantee? That you'll be able to, explain or express a function like this, which is again going to be a solution, right? So my point is that can you always find out U1 and U2 in such a way that if you again create a new function like this out of them, it is going to be a solution of this given equation 1. Okay, so the answer lies in the, yes, probably you have already got it. Answer lies in the functional independence of U1 and U2. That's what the next theorem is going to say. Okay, so and again, what they do, the next theorem, they like say they don't define it. They don't define it for the whole domain at the very beginning. Basically, what they do, they say that it is valid in a certain neighborhood of a point. Okay, but eventually, if you extend the neighborhood to the whole domain, you will see that it is going to work for the whole domain. Okay, fine. So let me see whether I can still retain this. Okay, B. Let me, instead of here, let me write 2 functionally independent solutions of this equation. Okay, and then the next thing is after this, I'll just simply modify it, order before that. After this, what I'm going to, I'm just saving some time. Okay. Let, oh, no, I'm thinking about using some different variables so that you don't get confused. In the book, they are using the same variable. I think it is fine. And let U be a solution of 1. Again, in this. Okay, see, here basically we are talking about 3 solutions. The first thing is that U1 and U2, they are functionally independent solution, right? And then I am talking about a solution U. It is simply a solution of the given differential equation, but I haven't described about any other property of this. Whereas U1 and U2, they are related by the functional independence between them. Is it okay? Fine? Okay. So then apart from this, let your x naught, y naught, z naught be a point in omega. Point in omega. So what the theorem is going to tell you is that what this theorem is going to tell you is that after this, so then there exists a neighborhood U of in omega. So that is your U is a subset of omega. U is a subset of omega such that this happens, such that U is this, such that U is this. Have you been able to appreciate the difference between the previous theorem and this theorem? Here, what is being told? Let me forget about U1 and U2. What is being told that you are given an equation given by 1, okay? You have a solution, right? Then, in the neighborhood of a point in the domain of definition of the function U, which is the solution, you would be always able to find 2 functionally independent solutions of the given differential equation, say U1 and U2, in such a way that U can be expressed as a function of two variables u1 and u2. Is it clear now? Is
Yes,
it okay?
sir.
Right? So let us try to prove it. Huh? So in between, I'm going to show you a theorem, which we are going to use. I'm going to stop in between, and then I'm going to show you the theorem, and then I will conclude. Just a minute. Okay, fine. So I'll be giving this equation. So let it be here. Let it be here. So again, we are going to use some knowledge of metrics. Okay. Okay. So since your this is true, u1, u2, right? Since they are solutions of this equation, so that is why I mean now you will understand why I wanted to use a different variable. That is why or maybe it does not look good. This is only for visual. And similarly, P plus R. Okay, fine. This is straightforward, right? Now, I mean, have you understood why I wanted to use a different variable for this? Because again, this U is kind of repeated, but I hope you understand it. Okay, fine. So now, what is it going to give me? What is it going to give me? Say, if I want to solve this one, in terms of say P, Q, R, PQR. So then this matrix say, so this is equal to 0, 0, 0, right? So basically what I have, I have something like some AX equal to 0, right? So now if you look at this one, and again, then you get X, then you then Y, then you then Z, right? So you see that what is this matrix? What is this matrix? It is nothing but the matrix of the Jacobian given by what? Is it okay? Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes.
And again, see, we have chosen the vector field in such a way that V is non-vanishing. V is non-vanishing, isn't it? Right? So that means at least one of the PQR is non-zero, right? Okay? So
Yes, sir.
yes, so that means this matrix, the determinant of this matrix what?
0.
Zero, right? Because if had this matrix had a unique solution, like say that is going to be only the zero solution because zero is already a trivial solution, right? So then I would have determinant of this matrix to be non-zero, right? I would have a non-singular matrix, right? But since at least one of P, Q, or R is non-zero, so that means this Jacobian of this matrix must vanish. Clear? Okay? So that is why this is equal to 0. Okay. Now let me come to another fact. So we have and see I have been giving you as any arbitrary solution, and u1 and u2 are two solutions in such a way that they are functionally, is it 0 bar?
0 bar.
0 bar.
Zero bar.
Right?
Yes.
So we have been giving that they are functionally independent, right? So far so good, right? So that tells you, and you know the components of this cross product, they were nothing but what? So basically, this was simply this. Yes? Right? We have already done this before. Is it okay? Fine? And because they are functionally independent, so this is non-zero, so that means at least one of these three components must be non-vanishing. Is it okay?
Yes, sir.
Right? So see now you see what like say information we have. The first information is that these Jacobian vanishes, right? And the second information is that see this is the Jacobian of third order 3, right? Second information is that the Jacobian, these three Jacobian of order 2, at least one of them are non-vanishing. Okay, so now let me show you a theorem. Let me hopefully, yes, I have that. Okay, so just give me a yeah, just have a quick look at this theorem. You see simply, I mean, theorem 3 is good enough. Theorem 3 is good enough. Like say the second part, the second part concerning with 3 variables. The next part, n equal to 3. You can start from that line. The generalization of theorem 3. What does it tell you? That you have a Jacobian of order 3 of 3 functions f, g, and h with respect to j. If it is neighborhood of some point x naught, y naught, z naught, and at least one of the Jacobians, this is non-zero at this point, it leads to a conclusion of the form that I can always have h expressed in terms of h is a function of 2 variables, right? And those variables are nothing but f and g. Is it okay? Fine.
Yes, sir.
Yes, sir.
Right? So I mean any one of them can be expressed as a function of the other 2 variables. Although the function of other 2 variables, I am assuming that it is a C1 function and it exists in the neighborhood of that point. Okay, that points mean that, like say u is simply equal to f of x naught, y naught, z naught here, and b is g of x naught, y naught, j naught. So now, have you been able to find the connection between these, generalization of this theorem to what we are trying to do? So obviously, this is nothing but inverse function theorem. Huh? So I could have simply concluded that from inverse function theorem, now we conclude that u can be expressed as a function of the two variables u1 and u2. Is it okay with everybody? Right?
Yes, sir.
Right? So you already have the statement of this theorem. So you got to believe me. And again, I don't have time to prove this theorem. Okay? So with this information in our hand, now we can conclude that from inverse function theorem, here u can be expressed as some function of u1 and u2, right, in the neighborhood of the point x0, y0, z0. So the proof is complete. Okay. So now, yeah, proof is complete. And again, see the solution procedure. You already know, right? It is simply converting it into dx by p equal to dy by q equal to dz by r. That's it. Okay, so let us try to walk up one example. So then I'm going to give you a generalization. Of the concepts of a vector field, then integral curve, etc. First integral in n-dimensional space. So you have to solve this. So solve. So now you know that, right? We have to find a function u which satisfies this equation, and that is equivalent to finding out a first integral of the vector field associated with this one, dy by y square equal to dz by z into x plus 1. So I think you'll be able to solve it, right? You'll be able to solve it. I don't want to spend time on this because you have already done it. Now you can relate this. Okay, fine. So finding solution of equations like this is simply solving this. But you should understand the geometric meaning of this. Okay, so now, okay, extension to n dimensions. I am just going to give you the kind of definitions. That's it. Okay. Okay, so now let me consider a vector field V in some region omega in Rn. omega in Rn. Okay, fine. So now a point in omega, it is going to look like this, right? A point in omega, it is going to look like this. So then, if you recall, see, when I defined a vector field in 3D, right? Its components, they were again functions of x, y, z, isn't it? Is it okay with everybody? I did it like this, right? So likewise, what I'm going to do, the vector in Rn. So now, what you must have n functions as components, isn't it? Right? Where P1 up to Pn, they are functions with domain omega in Rn. Is it okay?
Yes, sir.
Yes, sir.
Right?
Sir.
So now, can you tell me? Just a minute. And again, like say, this has to be non-zero. Huh? This has to be non-zero. This has to be non-zero. So now, as before, a curve C, I mean, it is going to be an integral curve of V, right? If at each point in omega, each point on C, each point on the curve C, right? V is a tangent. V is a tangent. Is it okay? Right? Is it? Are you getting my point? Yes?
Yes, sir.
So, can you visualize that? You won't be able to visualize it, I can tell you. I mean, more than 3 dimension, I can tell you that you won't be able to visualize it, right? But we can give some mathematical description of that. What is that? Like say, if you want to find out those integral curves, so then fortunately, what you are going to have what? An associated system of differential equations given by this, isn't it? Is it okay? Fine. So if I solve this, then I can find out that integral curve C. Agree or disagree? Agree or disagree? M dimension is creating a problem. Okay, fine. Before that, so maybe let me give you another information. So now, suppose I want to define first integral for the vector field v bar, right? So then the first integral say u, it is going to be a function of x, isn't it?
Yes, sir.
Right? So basically, this is simply x1, x2 up to xn, right? So in such a way that what is now, this has to be a first integral for the vector field v. So then what we must have your p1 du dx1 plus p2 du del u, sorry, del x2 up to p and del u del xn must be equal to 0. Is it okay? Fine. So u is going to be a first integral for the vector field v in omega if this is satisfied. Yes?
Yes, sir.
Has everybody got it? See, this is a simple extension to, this is simply a simple extension to n dimensions. That's it. Fine? So far, so good. Okay. So now, let me come back to this. So I told you that you can find a associated what system of differential equations given by this. Okay, fine. So now, like say again, see, I will be able to parameterize it. Appropriately. Parameterize it appropriately. So we already had a theorem for a function of 3 variables. Okay. So now, suppose by what did you do? What did you do for? Can you tell me? Now let me get back to this so that your confusions are not there. Okay. See, if by solving this, I want to find out an integral curve for v. What we did? We found two first integrals, isn't it? Yes. We
Yes,
found
sir.
two
Yes,
first
sir.
integrals, right? First integrals of v, right? And then if those two first integrals they are functionally independent, then what we did from there, we were able to find out a curve, right? So all those surface, like say the surface of the intersection of those two surfaces given by, say, if u1 and u2 are two functionally independent first integrals of v, so then what happened? u1 equal to c1 and u2 equal to c2, right? So their curve of intersection was nothing but the integral curve for v. Clear? Okay.
Yes, sir.
Fine. So now can you tell me how many first integrals I have to get? I have to find out in order to produce a curve.
N minus 1.
N minus 1. So, see, although I have written x here, in fact, there are like x1, x2 up to xn. You have to remember that. Okay? So, suppose I have found out this n minus 1 first integrals for v, right? So then I can derive an integral curve for the vector v in omega out of these first integrals if what? Earlier what happened? The gradient vectors, their cross product was non-zero. Isn't it?
Yes, sir.
Yes.
Right? See, from what we did here, grade u1, grade u2, we found out, right? And they were nothing but some vectors. In three-dimensional space, isn't it? Right? And their cross product being non-zero, signifies it as a physical property. They are not parallel, right? They are not parallel means they are, somebody already pointed out that day that they are linearly independent, right? So now, out of each of those, n first integral, they are nothing but functions of n variables. What we can do, I can get gradient vectors, grade u1 up to grade u n minus 1, right? So if these vectors are linearly independent, then we are definitely going to get what? An integral curve C for the vector field V in Rn. Is it clear now? Yes?
Yes, sir.
Right?
Yes.
So So that is what it is. Because now see, generally whenever we try to extend it to n dimension, we get a bit confused. But you just think systematically, or simply what you do, you write down all the concept for function of 3 variables. Just simply extend it to function of n variables. The only thing is that here these vectors have to be linearly independent. That is the condition which replaces the condition of the cross product of these two being non-zero. That's it. Okay, fine. So now let me try to work out one example for extension to 3 dimensions, sorry, n dimensions, how we can work it out. Okay, maybe I can write it down and after that I will do this. So this is the exercise. So you have to solve, you have to solve this differential equation. Solve this. So it is about solving this one. Okay, so I think the Thor hasn't given any name for those equations. Dx by p equal to dy by q equal to dz by r. I think you guys have we have grown up using the term, I mean, auxiliary equations, right? The auxiliary equation. So I mean, I can simply write the associated equations corresponding to this equation is what? Now we are going to have dx1 by x1 equal to dx2 by x1 x2 dx3 by x1 x3 equal to dx4 by x4. Okay. So now, can you tell me how many first integrals we will try to find out from here? In order to
Three.
get integral curve, yes?
3.
3.
3.
Or if I want to find out the general solution, see, okay, let me tell you just a minute. Let me tell you one thing. Earlier, when I talked about the general solution of, okay, so eventually we found out that, I mean, f of u1, u2, u equal to f of, well, this is a solution. So this solution is called a general solution. Okay, so that thing I forgot. So if I have to find out the general solution here, so I'll try to find out 3, I mean, first integrals. So if I look at the first two, what do I get? X1 is absent, right? So I am going to get x1 equal to ln x2, right? Isn't it? So basically from this, I'm going to get something like this. Am I okay?
Yes, sir.
Yes? Okay, so this is one integral surface. And then from these two, it is pretty straightforward. X1 goes. So this is going to give you simply x2 by x3 equal to c2, right? Because you are going to get ln x2 equal to ln x3 plus some constant, and from there you can get. And if I use the first and fourth, again, that is going to give me simply x1 by x4 equal to c3, right? So a general solution is simply given by something like this. You can simply write it like this: ex1 by x2, then x2 by x3, then x1 by x4. A general solution is given by this. That's okay. Fine. So now I'll be able to simply start. I mean, one concept. I mean, which is going to be very important. Which is going to be very important. Integral surface. Okay, integral surface. See, so far we have talked about integral curve, right? And whenever we talked about the integral curve, you have seen that it corresponded to a vector field V. Okay, so now I think that has already given you an idea how to define an integral surface. What was an integral curve? Again, I am in 3D. Don't worry about being in MD. Yes? Can somebody repeat me the definition of integral curve of a vector field V? Yes? What was that? A curve C in space, like say in some region omega in R3, it is called an integral curve of the vector field V if V is tangent at every point lying on that curve. Yes?
Yes, sir.
Yes.
Right? So then what will be integral surface? I am guaranteeing you that it is similar to this, exactly the same. Only thing is that, wow, now you are having a surface. So, yes, somebody is trying.
Tangent plane.
Tangent plane. No, but V is a vector field. Like you have to give me in terms of that vector V. Yes, plane. I mean, we may not have that plane right now. You take any point. Of course, I mean, you take any point, like say on curve, it is easier to visualize the tangent vector. Here, again, the same concept. Here, again, the same concept. Suppose I have a surface S, then if at each point of on this surface, I mean, V is a tangent vector, then we say that what? We say that
The
this
surface
S is an integral surface corresponding to the vector field V. But you are correct. Was it Sudharshana who was telling me about tangent plan?
Sir,
Manali.
I Manali.
Manali. Okay, fine. So, as Manali said, that there is a tangent plan, like say, where are you going to get the tangent vector, right? So basically, what you are going to do at that particular point, you are going to draw a tangent plan, and this vector is going to lie on that tangent plan. So then it is going to be a tangent vector. In that way, you are going to visualize it. Is it fine? Okay. So now, if I want to give a formal definition of I mean integral surface corresponding to a vector field V, so then how it is going to be? Again, that tangent line is now important. How it is going to be? Can you give me some idea? Can you give me some idea? I mean, just think when that tangent vector concept is going to be possible. Okay, fine. Firstly, let me give you an idea. Okay, suppose let's say S, not S, sorry. Let U X or J be a first integral of v say in some omega in r. Okay, fine. So now, if I create a level surface, say C, from that first integral, you know that first integral is nothing but a function. But if I equate the function to a constant, I get a level surface. Here, up to this, everybody is fine.
Yes, sir.
Yes. Sir.
Yes, yes. So then again, if u is going to be a first integral of the vector field v, then what must happen? What must happen? Your p, of course, I mean v is non-vanishing. Isn't it? What is the definition of first integral? First integral is this, right?
Yes, sir.
Right? This means that grade u dot v equal to 0. And what is grade u? What is grade u? I mean, if you consider grade u at a particular point x naught, y naught, z naught, then what is going to happen? What is going to happen? This is nothing but a normal vector, isn't it? Right? Normal
Yes, sir.
vector, right? Normal vector to this surface, to some level surface at the point x naught, y naught, z naught. Is it clear to everybody?
Yes, sir.
Right?
Yes, sir.
So
Yes,
now
sir.
you can visualize. Earlier, whatever information we had, that was kind of incomplete, or we were not able to, I mean, visualize it. But now see, suppose this is the surface, this u x y z equal to c. So now suppose I have taken this point x naught, y naught, z naught. Okay, so obviously normally you will be able to consider only when you are considering a tangent plane here, right? So then what happens? This is my gradient. Fine. So now if I consider say this plane which is a tangent plane on the surface u x y z equal to c at the point x naught, y naught, z naught. So then from this definition what I get, this vector v is perpendicular, this vector v is perpendicular, or this vector v and this normal is perpendicular to each other, right? They're orthogonal, right? So that means obviously that v must lie on this tangent plane, isn't it?
Yes, sir.
If any vector v has to be perpendicular to this gradient vector, which is normal, right? So it must lie on the tangent plane, right? So that means v must be a tangent vector. Is it clear now? Okay. So
Yes,
the
sir.
right, the formal definition is a surface S in a domain omega in R3 is an integral surface of the vector field V if S is a level surface of the first integral of V. That's it. That is good enough for all this information. Okay, so basically S is an integral surface of the vector field V. If what? If S is given by something like, or if S is nothing but a level surface of the first integral of V. That's it. And from there all these concepts come, isn't it? Is it okay? Fine. So I have already given the definition in the slide. So I'll upload them. I don't know whether it is in lecture 3 slides, but you again please go through. Please go through this TAW book, and let me tell you exactly what we are trying to do here. What we are trying to do here. Later on, we are going to develop some theorem. We are going to develop some theorem or concept based on the fact that suppose you know about a curving space, curving space. So now, can I generate an integral surface? Can I generate an integral surface of a vector field in such a way that this curve is always going to lie on that integral surface, right? So it is basically about construction of an integral surface of a vector field where you have it contains a given curve. That is what we are going to do. Later on, we are going to do that Cauchy problem, and you are going to have some initial curve. And somebody asked me, I think it was third one, about using, two parameter, right? Earlier, see, I had one parameter family of curve. Parameterization through two variables, right? You were asking about that. So now, whenever we are going to consider a surface, we are going to parameterize it through two variables. That is what you are going to see. Okay. So in my next class, hopefully I'll be able to touch upon that. Okay. And please again go through that book, TAW book again. You will see that your concepts are going to be crystal clear. Okay. So then I will wind up my class on that note today.